Okay, welcome to everybody that came face to face, and welcome to everybody who's watching online or watching later on. We are, of course, live streaming on YouTube right now. So if you have questions, you might please feel free to raise your hand if you're here. Otherwise, remember we are using Piazza for live Q&A. Remember that if you do raise your hand, that you might be picked up on the mic. I've got it pretty much isolated, but I will repeat your question. But understand that we are live broadcasting right now on YouTube. First of all, any questions from face-to-face folks that came? No? All right, then. Let's go ahead and continue where we left off on Friday. Or sorry, not Friday, but Wednesday. Anybody online, go ahead and tell me if I've got feedback, because of course I am coming through the speakers here, as well as picking it up on the mic. So we're going to continue where we left off last time by looking at variables and operators and the basics of programming. And so we kind of left off the details of what you should name your variables. And there are several variable naming conventions. First of all, there are several rules that you have to follow. That a variable's name, or sometimes we call them identifiers. That's the technical term, at least. A variable's name may consist of letters, that is A through Z, or A through Z, capital A through Z, underscores, right? The underscore right there, and numbers, right? 0 through 9. It may not begin with a number. And this is true of most programming languages, especially C-style syntax. It's difficult for a compiler or an interpreter to actually process a name if it begins with a number, because it starts thinking, well, this is a number, this is not a variable. It's we called those things literals. If you write int x is equal to 12, 1, 0, 1, 2, that's going to be considered a number, a literal, all right? So those are the basic rules, but there are some good conventions that you should follow. Good style means that variables should be named after the things they model. Right? So don't name your variable x unless it's standing for the Cartesian, in the Cartesian product x, y, z. If those are just points in the plane, that's perfectly fine to go ahead and name it x, y, z. But if it's representing like the number of students or something like that, don't name it z. All right? Or don't name it x. Name it number of students. Right? So use descriptive variable names. Right? For example, again, x might if it is a point or undefined, or if it's like a point or something like that, number of students, right? Or what's something else that we did? Miles, right? Or kilometers, right? Those are the good variable names because you didn't shorten them up, right? In general, avoid abbreviations, acronyms, etc., unless the context is absolutely clear. Okay? And by absolutely clear, for example, over here in the example that we already did, KMS, miles, well, KMS, that's an abbreviation, so I would want to avoid that in general. But in this case, it's okay because, the context is clear. I've got miles and I've got KMS. Well, that's probably kilometers, right? So the context is clear there, and it's perfectly fine in that case. Don't use placeholder names in real code, right? So for example, you'll see me using it all the time because I'm just doing examples of syntax. Foo, bar, baz, right? Or even worse, my variable. Or var1, var2, I need another one, var3, etc., etc. Those are terrible, terrible variable names. And you will be docked on stylistic points if you do that. In general, you should be consistent with your naming conventions. And the one that I'm going to suggest to you is to use lower camel casing. All right, lower camel casing. is a good one to follow. And you see how it works here. Lower camel casing, if it's multiple words like number of students like I already did, then you separate each word by capitalizing the first letter in each word, except for the first one. That's where the lower comes in, lower camel casing. You can also have upper camel casing, something like that looks like that, but that's used in different contexts. That's usually used for, in C at least, the modern convention that we'll use later on is using that to name an enumerated type or a structure much later in the course. For now, we're going to go ahead and stick with lower camel casing. Of course, there's always other styles that you can follow. You can follow lower underscore casing. That looks something like this. And that is an old school convention that's used a lot. The reason that I don't like it, and a lot of people don't like it, use the more modern lowercase convention, lower camel casing, is because what do you have to do to type that underscore every single time? You got to take your pinky and move it over to shift, and then all the way across the keyboard, hit the underscore, which is the hyphen, right? That takes a lot more to type, and of course it starts giving you pinky strain. So save your pinky and use a more modern lower camel casing convention. Whatever you choose to use is perfectly fine. You just have to be consistent about it. All right? You shouldn't use one casing for one variable and then a different casing for another variable. In this case, I am following lower camel casing conventions. It's just that there's only one word here, or an abbreviation, like in this one, and so it's all lowercase because there's only one word. If there were multiple words, of course, each word after that would be capital. The first letter would be capitalized. Okay. All right, so that's a little bit of styling. Let's talk a little bit more about there we go. Let's talk a little bit more about operators. All right. We've already seen the assignment operator, the equal sign, where you can take a value and or an expression or something and put that value into a variable on the left-hand side. That's used all over the place. Unfortunately, it's a single equal sign. It was misused 50 years ago. It has a meaning in algebra that has a completely different meaning here in coding. Most programming languages use the single equal sign as the assignment operator. Okay. But other operators that you might have already seen are arithmetic operators. Right? The plus, right? Addition, subtraction. And unfortunately, we don't have a times. I mean, we have x, but that's x. That's not times. We don't have the time symbol or the center dot, like if you had an algebra. Here, I'll just write it in LaTeX really quick here. A times B, right? It would end up looking something like that if you were writing this as math, or it would end up looking something like C dot. There we go. Something like that for multiplication. We don't have that on the standard QWERTY keyboard. So instead, we have a placeholder, you know, the star, right? The asterisk. And that's multiplication. Division, also, we don't have the, whatever this thing is called, right? Div, right? Something that looks like that. We don't have that on our standard keyboard. So what we have to do instead is the next best thing. And tell me, is that a forward slash or a back slash? That's a forward slash. Why? The guy's facing that way, he's leaning forward. A backslash would be he's leaning backwards when he's facing to the right. Right? We have a can't find the Zoom link or live session. As always, we're on YouTube. Right? We are broadcasting, are we not? I don't know, is anybody watching it live in here? All right. Yeah. All right, so question answered. Yeah, I've got actually amazing zero drop frames. Awesome. All right, very good internet today. All right. So consider the following. What if I wrote the following, if A, B, and C were all variables, what if I wrote A plus B times C? All right, is that the same as A plus B in parentheses times C? And I'm going to go ahead and give myself some nice white space so that it's nice and readable. Are those two the same things? Would they be the same thing in algebra if you wrote those down? Instead of the asterisk, it'd be the multiplication. No, why? What? I can hear you because I got open backs, but order of operations, what do we call that in basic arithmetic? What's the order of operations? There's a mnemonic device for it, or an acronym for it. PEMDAS, right? That's parentheses, exponentiation, although you don't have exponentiation, you have to call a function to do that for you. Multiplication, division, addition, and subtraction. Same thing in code. Parentheses will elevate the order of operations. Multiplication and division are done before addition and subtraction. And so these are not the same things. In this case, it would be b times c first, and then that value would be added to a. In this case, we put parentheses there. So it would be a plus b times c. Same thing as in algebra. Nothing changes. So you're not paying by the character. Go ahead and write parentheses even if they're not necessary. If I were writing a times b times c all like multiplication, 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 then I wouldn't put parentheses. But if I were doing something more complex, I sure would put parentheses in there to collect things even if I didn't have to. Because it makes it more readable and sends out your intent. This is what I intended because this is what I wrote down. Okay? So keep that in mind, that we have PEMDAS in coding as well. Another example, let's see. Let's take a look at some, actually, no, let's, one more operator here. Another operator is the integer division operator, right? The percent sign, right? And for this, I'm going to go ahead and jump over to another tool here. This is called REPL. It's an online website, repl.it, replit.it, and it has support for many languages. And it's kind of like an IDE, like CS50 over here, except that you do have to sign up for it to save everything, but it's not as full-featured in my opinion, because over here you can actually install stuff like you did in Lab 1 or Hack 1 or whatever it was. But you can run quick code, just quick code samples here. Let me go ahead and create an integer variable here. A is equal to, 13. And int n is equal to 2. Right? So now what would happen if I do a divided by n? Let's change this to 14, right, for now. So int result is equal to a divided by n, or n, there we go. And we'll get to output here shortly, but what if I wanted to print this out? Result is equal to %d is a placeholder for an integer. Again, we'll talk about this in a second. I'm going to print out the result here. 14 divided by 2, what should the result be? 7, okay. What if I said that this was 13? Now, think back to grade school, and you have 13 divided by 2. How would you write that out, long division-wise? So 2 goes into 13 how many times? 6 times. And then what else do you write over here? A remainder of 1, exactly. And when I use the percent sign instead, it doesn't mean percent, it means integer division. It means percent gives you the remainder of the integer division. So in this case, 13 divided by 2, the remainder is 1. What if it were 14 divided by 2? What's the remainder then? 2 goes into 14 how many times? 7. Remainder of? 0. So no remainder. What if it was something else? What if it was 3? What if I divide by 3? What are the possible remainders of division by 3? 0, 1, and 2. Why is 3 not a remainder possibility? Because 3 goes into 3, so you'd have to go in another time. So 14 divided by 3, 3 goes into 14 4 times, with a remainder of 2. What if there were 15? Well, 3 goes into 15 5 times with a remainder of 0. And what if it were 16? 3 goes into 16 5 times with a remainder of 1. So the percent sign gives you a remainder. And it also gives you a way to detect whether or not something is even or odd, or divisible by 3 or not, right? Or other things like that. So the percent sign gives you a remainder. Here are some more examples. If I divide 10 by 3, that results in 1 because 3 goes into 10 3 times with a remainder of 1. 11, mod, we call this mod, or this is the modulus, right? Also known as the modulus, or simply mod operation, right? Because you're taking mod and then you're given the remainder. Okay. PEMDAS doesn't work. So does it not use PEMDAS? It goes left to right. Yeah, it goes left to right on all of the arithmetic operations. It does use PEMDAS. Right? That was a question online there. Why does the machine compute the sum first? Because, well, for this one, I assume that they're talking about is because the P in PEMDAS. P stands for parentheses. So if you put parentheses around something, that elevates the order of operation to first you do everything in parentheses, then you work outward. Okay. Code from the bookstore. How do you get the code from the bookstore? Anybody? Yeah, pay for it, right? So you go to the bookstore. I can't help you with bookstore stuff, right? All right. So here's another pitfall that many people are already experiencing on Lab 2 because we designed Lab 2 to illustrate this. Truncation. Right? So I'm going to go back over here to my demonstration. I'm going to make these into A and B, A divided by B. Right? And I'm not going to use the modulus operator. I'm going to use the regular old division operator, A divided by B. Right? And let me go ahead and print out the result here. Now, algebra-wise, 10 divided by 20 is what? 0.5, right? Well, what do you think is going to happen here? 0. Why? Something happens when you do an integer divided by an integer in a lot of programming languages, including C here. Right? So again, here is the example that I just did. That if I have, int, there we go. This results in 0. When you have two integers in your arithmetic operations, the result is always an integer. Right? And that doesn't matter too much when you look at 3 of those operations: addition, subtraction, and multiplication. You add 2 integers together, you get an integer. That makes sense. 4 plus 4 is 8. You multiply 2 integers together, 2 times 3, you get an integer back. But what happens when you divide an integer by an integer? If you divide an integer by an integer, the result must be an integer. Right? So what happens is the fractional part, right, in this case 0.5, gets cut off and thrown away. Right? This is known as truncation. So it's just a quirk of the language. It's a quirk of a lot of programming languages that don't have dynamic typing. You'd also have this in Java. You'd also have this probably in C++, probably C# as well, etc. You don't have this in a programming language like, say, Python or PHP or JavaScript, because what they have, well, first of all, some of those don't even have, JavaScript doesn't even have an integer, I believe. It just has one type number. And all numbers are end up being able to be fractional numbers. But what you have here is truncation. Truncation. There we go. I spelled it correctly there. Right. So what happens is, again, it gets chopped off and thrown away. It's not rounding. It is not rounding. It is not flooring. If you know what floor is, 1.4. or the floor of that number, you just take it down. Rounding goes up by halves. 1.5 would be rounded up. 1.4 would be rounded down. It's not rounding. It's simply taking that fractional part, everything after the decimal point, and chopping it off and throwing it away. Okay? You can solve this problem by temporarily making one or both of your operands compatible with a double value. Remember, double values are those floating point numbers. 3.14, 1.5. 10.0 is still a floating point number as long as you have support for that, that fractional part. And this is called using typecasting. All right? So I'm going to go back over to my example here. And of course, I'm going to have a double value here in order to store this, because if this is an integer, it doesn't matter what I assign the value to, it's always going to truncate. I need a double value here to hold a fractional value. This is still going to, and now I need to change my placeholder here too, we'll talk about that in a moment. But this is still going to result in 0, even though result is now a floating point number. It can take on that fractional part. The problem is what's on the right-hand side, that still results in an integer. So what I can do is I can force one of these things to temporarily become a double by putting in parentheses a new type in front of it. You could do it to both if you really wanted to, but that's overkill. You just need to do it to at least one. And now the result is going to be 0.5, the correct result. This does not change the variable b. The variable b is still an integer. It still has 20, the value of 20 in it. It can't be 20.5. It can't be 20.0 even. It's still always going to be an integer. All this is doing is saying temporarily treat b like a double value for the purposes of this division so that we don't lose that fractional part. Okay? That is typecasting. You are casting the type as something different. And so I'll go ahead and copy and paste this example as well, right? So that it's in the notes. Also, you have math library functions. The math, where's the math library again? What do I have to include? Math.h. Wow, just like it says in the tin, right? Has a bunch of nice mathematical functions. For example, sine, it's S-I-N-E, cosine, tangent, square root, right? And you'll notice that a lot of these are abbreviated. Remember we said abbreviation should be avoided in general. The reason that these are abbreviated is because they're old. Like I said, today we're not paying by the character. You can make your code as long as you want, although you should not make it just super, super long variable names. But S-I-N, well, why didn't they have an E there for sine? Cos, why didn't they have an I-N-E, right? Why don't they spell out square root? Why do I have to remember that the abbreviated form is SQRT? And it's because 40, 50 years ago, they did pay by the character. You now have routinely hard drives that are in the terabytes. This one is, my computer's 4 or 5 years old, and I still have a half a terabyte. I have external drives over here that are 2 terabytes, and they cost me less than $100. All right, storage is super cheap now. But that wasn't the case 50 years ago. If 50 years ago, where you measured hard disk space on and computer memory in kilobytes, if you could save a character, you definitely did it. We're still paying for that today because most math libraries, even in modern languages like, say, Java, will still use these same basic abbreviations. What's available? Remember I showed you the man pages last week, or you could just use your old friend DuckDuckGo, right? Math.h. There we go. Don't use Google right? Unless you want them to follow you. And here's math.h. Tutorials point, you probably don't want to use them, but they will. They do at least list all these things, like the arcsine, the 2-argument arctangent, right? Cosine, hyperbolic cosine is in there, et cetera, et cetera. Everything that you would basically find on your scientific calculator is going to have some sort of implementation here in the standard math library. Okay. All right. It also has nice constants. It's already defined pi, and it's pi, m, e. Just like over here in our example that we were working with last week, I decided to go ahead and define kms per mile as this value right here. Well, the math library has already defined pi out to as many decimal places as are accurately representable in a computer. So you don't need to use your own definition of pi. In fact, you shouldn't use your own definition of pi because yours is probably going to not be as accurate as the one that's built into the library. Or E, that would be 2.71, et cetera, et cetera. Let's check some questions. Let's see. PEMDAS doesn't work. Oh, okay, I did answer that one. Okay. If you are asking questions about hacks and books and stuff online, you might want to make your own thread because we're not going to see it in the live Q&A here. The live Q&A is for stuff that's going on in lecture at the time. So make sure that you're following up through a proper channel here. Okay. All right. And of course, you can include it by using the math library. If you work on CSE, you may need to use the LM flag to compile with the math library. If you are using CS50, you don't have to worry about this quirk. If you are using the CSE compiler, if you're using like Terminal or PuTTY, then you may need to use the LM flag. That would look something like this. I'll just go ahead and like if you've got my program, you would use GCC-LM my program. And just to let you know what this does, it's a flag that says link in the math library. So LM link in the math library, and it's just something that's a historical quirk. The math library is special because they thought 40 years ago everybody's going to want their own special math functions. So we'll make this slightly different, right? Again, if you are on a more modern system like CS50 or something, then you don't have to worry about that. Our setup is a little bit different on CSE, and it's just a gotcha thing that you might need to use. All right. So RTM. What other functions may there be? RTM. All right. What does RTM stand for? Anyone? RTM. Read the manual. And then you can always, of course, be more forceful and say RTFM, and I'll leave you to guess what F stands for. All right? Freaking, right? All right, any questions so far? No? All right. I don't see any new ones online, so let me know if anybody's following along online. You were probably on a 10-second delay anyway, but if there are any technical issues, please bring those to my attention too. So basic I/O, I stands, of course, for input, and O stands for output. Right? What we've been using up till this point in this program over here is interactive input. With interactive input, a program prompts the user to enter a value, then reads the value from the user, right? In other words, the steps there are that when prompted, the computer will block execution. In other words, it stops execution and waits for the user to mash their keyboard and then hit enter. After they've hit enter, that's when the computer takes back over, the program takes back over, and starts saying, oh, what did they enter? All right, they entered 1, 2, 3, so I read in 1, 2, 3. So let's go ahead and see this in action over here, and let's see, where am I? Nope. So another thing that we've seen online people trying to do is that they've been trying to compile this KMS 2 miles program. Oh, no input files there. Why? What's going on? Well, this file is located in this directory called code. I'm not in that directory. Where am I? I'm in home Ubuntu. I need to go into this code directory right here. I need to change directory into that code directory. ls means list all the files that are there. There's that hello file from Wednesday, and there's the KMS 2 miles program that we were working with last week. GCC KMS 2 miles, and that produces an a.out file. And when I run that, please enter miles. Remember that it is prompting me to enter the miles. Okay, I'll go ahead and say 100 miles. How this worked was the scanf was scanning the input. And what that means is it's blocked execution. It stopped executing, right? it prompts and then it stops executing so that I, as a human, I'm much slower than a computer, I have time to actually sit there, type, and mash my keyboard. Of course, I won't mash my keyboard. I'll just go ahead and be nice about it and actually enter in an integer that I know that will work. After I hit enter, the computer takes back over, scans that input, and puts it into a variable called miles. Then it goes ahead and computes the multiplication of that, and then it prints this out, and at which point the program is done executing. And control is returned back to the operating system right here. All right? What happens, well, before we talk about the details of this, what do you think is going to happen if I am a keyboard masher and a 10, T-E-N? Kill the program? Blow up the computer? Let's find out. I'm willing to risk it, are you? All right. 0. Why did it read 0? I entered T-E-N. T-E-N is not a number. It's expecting a number here, and we'll talk about this placeholder here in a second. It starts looking, it did the process that I just described. It looks at the input and said, after I hit enter and said, all right, what's entered? T? Well, T's no number I ever heard of. So what have I read so far? What has the computer read before this? Right here. Nothing. So what's the numerical value of nothing? 0. And so 0 miles is 0 kilometers. Right? What if I did something else? What if I said, oh, I don't know, what is 100 billion miles? So 100 millions, thousands, zeros. What's going to happen now? That's a valid number, right? Oh, darn it. It's going to work because it's a double. Everything's a double. Darn it. Okay. Anyway, one thing that you'll notice in lab 2, I should have put int over here. Right? Int. But then I wouldn't be able to allow you to enter fractional miles, like 10.5 miles, right? 10.5 miles is whatever. If I had made this an integer, would I be able to store 100 billion? No, why? Remember the limits that we talked about on Wednesday up here, right? An integer can only represent about negative 2.147 billion up to positive 2.147 billion. So if I enter 100 billion, that's going to result in what's called overflow because you went past the maximum amount that is representable. Right? You'll get a lot more practice with that in tomorrow's lab. Okay, that's just an aside there. Okay, so input. For interactive input, you use scanf, which stands for scan the standard input in a formatted manner. Right? That's what the F stands for. So you're scanning formatted. Right? The format means you can use one of several placeholders, right, depending on the variable type you want to read in. So for example, if you want to read in an integer, you would use %d. All placeholders begin with a % sign. If you want to read in a double, what did I use over there? What placeholder am I using over here? LF, right? And LF stands for a long float. Right? Don't worry about, oops, % sign, not dollar sign. LF stands for long float. Don't worry about it. Just remember a double is associated with LF. It's kind of weird though, right? D, well, double should be D because double starts with D. And integer should be I, and I agree with you. That's wrong. That it looks terrible, but it is what it is, right? And we have to live with it. Right? I could improve this if I went back in time 50 years and hit Kernighan and Ritchie over the head with something and told them, no, don't do that. Right? Otherwise, 50 years from now, I'm going to have to explain to students that it was wrong and that we're living with it today. Right? So a character is the only one that makes sense, unfortunately. If you want to read in a single character, like a yes or a no value, then you use %c. Right? All right. In general, you only read one value at a time. Right? Never forget the ampersand in front, ampersand, that's, I spelled it right, in front of the variable you want to store the value in. For now, magic. It's magic. It's necessary because it's magic. Something magic is going on. Now, for a little bit better explanation here, this ampersand is necessary because we have to pass this variable by reference, meaning that we have to pass its memory address to this function right here. Otherwise, it will not be able to store the value that it reads, 10.5 into this variable. If I wanted to read it into a different variable, I could have read kilometers instead by putting the variable name over here. But I wanted to read it in miles because I'm converting miles to kilometers, not the other way around. If I were to rewrite this program the other way around, convert kilometers to miles, then of course I would read in kilometers and print miles instead. Okay? Just don't forget the ampersand. If you do forget the ampersand, good compilers will remind you and warn you about this. So let's go ahead and try to compile this, KMS to miles. And warning, %LF expects a type double, but argument 2 is of type double. In other words, you forgot your ampersand. Right? It's complaining about this now. In fact, it's just a warning. It'll still run. It'll still prompt. But when I give it an answer, hopefully that's going to be a darn it. It should have been a segmentation fault. Generally, if you abuse memory like this, you will end up with what's called a segmentation fault. In fact, maybe I can force it equals negative 0.3. Let's try this. And yeah, warning. 10.5. Aha, no. All right. Tricky. All right. Just don't forget the ampersand. Right? It's magic for now. We'll explain it later when we get to functions, passing by reference, and pointers. Okay? All right. What about output? Oops. Basic output. You can use the standard, you can print to the standard output using printf, like we've seen. And that stands for print formatted. Same formats. You provide any number of placeholders and a comma delimited list of variables to whose value you want to print. Right? So those placeholders that you've seen before are the same placeholders. If you want an integer, then you would use %d. There we go. If you want to print a double, it is a little bit different here. %LF will probably work, but it's more usual to use %F. And finally, if you want to print a character, then you print %C. There we go. There. But when printing numbers, you can you have more fine-grained control over how many columns to print and how many digits of accuracy you want to print using placeholder modifiers. Right? And so I'm going to look at this from the most general that you can use, %n.mf. Okay? So for this idea, let's go ahead and go back over here to REPL. And what I'm going to do is, disconnected. Now we're connected. All right. Oh. There we go. Now we're reconnected. We're not dropping any frames, are we? No, we're still good. So I am going to define my own. Actually, no, I'm not going to define my own pi. Let's do it. All right, double pi is equal to 3.14159. Again, I should not do that in general. I should use the math library's pi. Include the math library. And then I could go ahead and use not pi, but m_pi. Right? So let's go ahead and print out pi. Pi is equal to %f, just by itself, m underscore pi. All right. Now what this is going to do by default, oh, why don't you know where you are? Okay, well, let's find out if this works. Okay, it's still working. It's because it's a preprocessor directive. REPL's not smart enough to figure that out, but the compiler over here is perfectly fine with it. All right, so let's go ahead and have some more fine-grained control over this thing. So by default, the default behavior of printf is to always print out the entire number, but only to 6 digits of accuracy. What if I want more digits of accuracy? What if I wanted, say, 10 digits, 10 decimals of accuracy? Then I can use the following format. Pi is equal to %.0 or .10f, and then I'll end the line. Remember /n, that's just to end the line, m sub pi. There we go. This will print out 10 decimals of accuracy. And we've got 14159, 26536, excuse me. Right? Is that correct? How many people know pi out to more digits than that? You know? Okay. I don't know either. Who cares? Right? If I wanted 15 digits of accuracy, then I would put 15 here. If I wanted 1,000 digits of accuracy, do you think I'm going to get that? Remember, what's the limitation of a double that we looked at last week? Here we go. Where are we? Limitations. There we go. So a double, how many digits of accuracy does it have? About 16 to 17. So what's this going to print? Right? A bunch of zeros after. Right? There are about 16 reliable decimals of accuracy here, after which you just have a bunch of zeros because it can't represent it anymore. But it'll happily print those zeros out for you if you really want it to. Okay? So don't do that. Now, what if I wanted to print, say, 10 digits of accuracy, but what if I put 20 in front of it? Remember, this is % period for the decimal point, and then however many digits of accuracy you want after the decimal point, and then an F for floating point number. What if I put a 20 in front of it? Let me go ahead and print this out and see what happens. All right. Still going there. Clear this. All right, come on. There we go. All right, it just needed time to think here. What did it end up doing? It ended up indenting it a little bit. What this is doing is it's saying, I want 10 digits of accuracy, so I'm going to get exactly what I had before up here. 10 digits of accuracy to the right of the decimal place. But this is saying print a minimum of 20 columns. So if you take a look at this, this is 1, 2, 3, 4, 5, 6, 7, 8 columns. The 3 is the 9th column. The period counts as a column. So that's 10 columns altogether right there. And then 10 columns afterwards. So I was saying print at least 20 columns. And it'll do so by indenting however many columns it needs to pad that out to 20 columns. Now, if you say that you want only a minimum of 2 columns, then I'll get the same behavior as before because, well, okay, I'll print out 2. Actually, I have to print out 12 columns here. So by doing that, I've already met your minimum standard. The reason that you would use something like this is so that you can, align things like a ledger book or something. If you want all the decimals aligned, regardless of how many digits of accuracy to the left or the right, you can exploit printf to do something like this. It also works with integers. Int x is equal to 123 or 1,234. Printf. What's my placeholder for a decimal value? What was it? %d, end the line, x. And that'll print out 1,234. But I can also say I will print out a minimum of 10 columns. And now it'll pad that out with how many columns are there without counting them. 6. Why? It prints out 4 decimals, and I said that I wanted at least 10 columns, so that's 6 places up front. You can really play with this if you really want to and do variations. I don't want spaces as my placeholders. I want zeros as my placeholders. And then it'll pad it out with a bunch of zeros. You can This is right justification. You can go left justification, right? That where you go -10. Now you can't see it, but I'll add something in hello, right, at the end. And you can see that it put those 6 additional spaces on the right-hand side instead because I gave it a -10. So there's a whole bunch of things that you can do with this and that you can play around with it and get it to print whatever formatting you want. That's why it's named printf, right? Print formatted. I'll go ahead and cut and paste this so that you have it in the notes later. Oops, there we go. There we go. Now that's in the notes. Any questions so far? No? Let's check online. All right. Again, if you're asking questions like credentials and stuff like that, the best place to ask that is in the main room, not in the live Q&A. Okay. Okay. Let's see. What about non-interactive input? Okay. Interactive input is where the computer prompts the user for an input, and the user sits there and mashes their keyboard, and then the computer pauses for them to mash their keyboard and hits enter, and then reads whatever they typed in. Non-interactive input is where you are reading the input values directly from the command line. These are arguments are provided to the program from the command line, right, as command line arguments, or CLAs. Right? Okay. No interaction with the user. There's no prompting, no reading. The program reads them when the program starts. And actually, this is the usual way the programs actually run. The vast majority of software is not intended to interact with a human. Something like 99% of all software is written to interact with other software. People have this misconception of what software is for because mostly they're consumers. They're consumers of software and they're consumers of products. And so they see this nice user interface with bright, shiny buttons and input boxes and all that stuff. And so that's what they view when they think computers. The vast majority of software is never intended for another human at all. The vast majority of software is intended to interact with other software non-interactively. The program is not sitting there waiting for somebody to mash the keyboard. It's sitting there listening to another program or talking to another program and going back and forth. We won't get into it too much, but I will show you how to do this non-interactively. So I'm going to go ahead and create an alternative here. So I could go ahead and create new file, cut, paste everything over to that new file. But I'm going to take this opportunity to show you another command line command that you can use, CP, which stands for, it's shortened for copy, right? It means copy, but you don't use copy, you use CP. You can copy KMS to miles, and note that I didn't type all that out, right? KMS to miles, here's another trick. As long as you have a few of the initial letters, hit tab, and it's command completion for you, right? And you don't have to sit there and type every single thing in the CS50, or any command line for that matter. I'm going to copy that file into another file, KMS to miles, but with a different name, command line arguments.c. And you see up here that now you have two files, kms to miles.c and kms to miles CLA.c. I am going to convert this over to use command line arguments instead of prompting for input here. Now there's only one argument that the user is going to provide, and that's miles. So I'm going to go ahead and take away this prompt here. I'm going to take away the scanf because I don't want to read interactively. So how do I get that argument that the user provides into my program? That's where these things come in. argc stands for argument count. argv stands for argument vector. Okay, so command line arguments are provided by the argc, which is the number of arguments. That's the argument count, right? And count, and argv, the actual arguments, the vector of arguments. That's what the v stands for. It's just a vector. Not vector calculus, but vectors as in mathematics. A vector is a tuple, right? If you have a three-dimensional vector, then you have x, y, and z. If you have an n-dimensional vector, then you have n scalar values. This is a vector because it's a list of values that's ordered. There's the first argument, the second argument, the third argument, etc. Some notes here, though. argv sub 0 is always the program, or the executable program name. Right? That's never the first argument. argv sub 1 is the actual first argument provided by the user. Right? And thereafter, of course, argv sub 2 is the second, etc. Right? So you can provide as many command line arguments as you want, and of course they'll be just numbered. The first one, the second one, the third one. You use this the square bracket notation because that's actually an array, and we'll talk about arrays later on. So what I want to do here is I want to read in that vector, read in that value. So the miles provided as a command line argument will be stored in which one? argv sub 0 or argv sub 1? Which one? 0 or 1? Which one's the actual first one? The 0 is always going to be the executable program name, like a.out, right? So I'll put that in the notes here. Example, a.out. That's not going to tell me anything. That's not going to be the miles. So what do I want? I want argv sub 1, the first one actually provided by the user. Right? Now I'm going to convert the value to a floating point number. And to do that, I'm going to go ahead and use this function called a to f, right? argv sub 1. A to f, a to f. Well, I'll tell you what the a stands for. It's alphanumeric. In other words, it's a string. 2 is a conversion to a different format. What do you think the f stands for? Floating point number, right? And so I'm going to convert whatever they provide at the command line to a floating point number so that I can store that as miles. And I'll put that in the notes over here. You can convert arguments using a to f to convert to a floating point number. In other words, a double. Right? You can use another one called a to something, a to, I don't know yet, you tell me, to convert to an integer. Right? In other words, an int. So what do you think that one's called? Unlike printf, it makes sense. I'll give you that hint. A to what? A to I, right? A to integer, right? Otherwise, maybe whole number or maybe a decimal number or a digit, right? But a to I is what it is, okay? What I've done over here is I've converted the first actual argument to my miles. Now let's go ahead and compile this program and see how it works. KMS to miles, CLA. There we go. Everything's fine. No news is good news in Unix. And I'm going to go ahead and say, well, I want to convert 100 miles to kilometers. Oops, sorry. Oh, darn it. All right. I edited KMS to miles. I should have been editing CLA. Right, there we go. So I'm going to have to swap these two around. I'm going to take this opportunity to show you another command line command that you can use. MV. MV stands for move a file. So I'm going to move KMS to miles, CLA, to temp.c because I want to rename the other one. I want to move KMS to miles KMS to miles CLA.c, and then I'll move that temp file back into KMS to miles.c. So I'm just moving files around, and you saw how that worked up here. I moved one into a temporary file, I moved the other one into the other file name, and then I swapped the temporary file and that one back. And now, I'm going to go ahead and, CS50, sorry about that, but the 50 IDE. There we go. Out of habit, I hit Control W. You might get into this habit as well. Control W to close a tab is almost universal. Well, guess what tab I closed? The browser tab, not the IDE tab up here. I have to get out of that habit here. Otherwise, I'm going to do that over and over again. So let's go ahead and compile it, KMS to miles CLA. And I'll run it here. And I want to convert 100 miles to kilometers. And it works because what happens here, I need to close these and refresh, or at least refresh them. What happens here is it doesn't prompt me for anything, right? It doesn't block and then read the input after I've mashed the keyboard and hit enter. It immediately goes to these command line arguments here and says what was provided at the command line. 100 was provided at the command line. I'm going to convert that to a floating point number, place that value into the miles variable, and then do the rest of the calculations like normal. If it's 100 if it's 10.5, we'll see what we got before. What if it's TEN? What's your prediction here? 0. Why? Because it sees T. That's not a number. What have I parsed so far? Nothing. What's the numerical value of nothing? 0. What if I don't provide any command? Oh, let's try this. What if I provide 3 command line arguments? That's okay, because I'm only looking for the first one. So 20 and 30, they end up getting ignored. But what if I go the opposite direction and don't provide enough command line arguments? I'm not providing input here. What do you think is going to happen now? Now it's a segmentation fault. Segmentation fault means that you are doing something extremely illegal, and the operating system caught you, and the operating system is not going to let your program do something extremely illegal, like accessing memory that doesn't belong to you, and so it segfaults out. A segmentation fault, a segment is a segment of memory that your program is trying to access, that it doesn't have permission to access, and so the operating system kills your program. Right? It's a fault, all right? So I'll be nice about it and always provide command line arguments. Well, how could we program this so that if somebody does screw up, that we give them maybe an error message? We can check to see how many command line arguments there are by doing an if statement, a conditional. If the number of arguments is not equal to 2, and this is the next topic that we'll get into on Wednesday, then we'll go ahead and printf error. You must provide miles. Right? And then we're going to quit on them. I'll explain all of that next week. Let's try it out here, though, today. All right, let's go ahead and another tip. You can go ahead and hit the up arrow. You don't have to retype everything. The up arrow, and that goes through the history of your commands. Let's do this again. 100. Okay, that works. I can even go 10.5, and that works as before. But now if I go ahead and don't provide any command line arguments, or if I provide too many, then it's going to give me an error message instead of that illegal segmentation fault kind of thing. And this is defensive programming. I'm checking to see if it was legal input, expected input, and if it's not, then I'm giving them an error message and I'm quitting. I'm exiting the program. We'll talk about what 1 means here later on. Okay? That's non-interactive input. Any questions so far about any of this? No? Yeah, go ahead.
Okay, so when you say non-interactive, in like the grand scheme of things, you still have to input as a user just before the code begins executing.
True.
It's still an input, but it's not a stopping and executing the program and then resuming the program.
You got me on semantics, exactly. So there is still an element of somebody inputting something into the program. It's just they do it at the command line, and so that there's not this interaction. You might have seen that like in the video where I install stuff on CS50. I put in a flag that said, just say yes to everything. Don't bother asking me. Don't bother doing interactive input. I think it's -y. When some people were doing it by themselves, they didn't put that in, rightfully so, because I don't think I mentioned it. But then they freaked out because now it's asking me a question, yes or no. Just go ahead and hit yes. It's just a difference of interactive versus non-interactive. There's still input in some sense. You still have to have input. Now, if you have another program that is doing some calculations and then feeding that into another program, then of course the program is responsible for the interaction. But still, maybe a better term here would be a non-human interactive program. All right. So yes, there is still input. Every computer program is going to still have input of some sort. Unless it's just a constant program that does the same thing every single time. It prints hello world, for example. Okay? All right, in our last 15 minutes here, let's do an exercise. Right? Let's go ahead and make another simple program. Exercise. And this is the one I usually do. Write a program that reads in 3 coefficients of a quadratic polynomial and outputs its roots. Right? So in other words, x squared plus bx plus c is equal to 0. Look familiar? How can I find the roots of that equation? The quadratic formula, exactly. All right? So let's go ahead and write this program. I'll call it roots. All right? New file, roots.c. Oh, wait, before I do that, let's go ahead and cancel that. Untitled, okay, remove that. Here, how do I remove files? Do you remember? rm, untitled. Be careful, removing things, they're lost and gone forever. All right? There is no undelete at the command line. There is no recycle bin at the command line. There is only what we call dev null. ls dev null. Right? Dev null. What's in dev null? Nothing. Right? Absolutely nothing. Dev null is where things go to die. Right? It has it's nothing more than a permanent black hole of waste. Anything that you throw down there is gone forever. That's basically what happens when you remove something. It is gone forever, never to return. This is why we use systems like Git, so that you can check in code and you have a whole history of all the changes that you've made, and you've got a second copy somewhere up in the cloud. Okay? The purpose of us introducing you to Git in the first week is so that you use it throughout the semester. Because inevitably, we always have somebody that's, I spent 10 hours on this program and now it's gone because I accidentally removed it or I accidentally overwrote it. Well, that's why you use Git. Right? And now, if you use Git, you've got versions of it going back however long you've been committing. Right? Use it to the fullest extent. Right? Because you do not have a recycle bin or an undelete or an undo operation at the command line. All right, let me go ahead and make that file. There's another command called touch. If you touch something, it magically comes into existence. I'll call this program roots.c. Right? And it magically came into existence. What's in it? Nothing so far. But I can create, otherwise I could have just right-clicked over here, a new file, that's boring. Go ahead and touch it, right? And you recreate it. Let me go ahead and start. How should I start my program? What should be at the top of every single program? Documentation. Right? So, author, me. Right? One thing that we saw way too often was people did not change the author of their Hello World program. We didn't take off points for it. We would on a hack, but you definitely need to make sure that the author is correct, or authors, right? Date, 2020, what is the date? 24th, there we go, oops, there we go. And what's the purpose of this program? This program reads in 3 coefficients of a quadratic polynomial and computes its roots using, what did you tell me? The quadratic formula. Yay. End it. Okay. What's the next thing I need? I need to include my external libraries. stdlib. I'm probably going to be doing input and output, right? So I need to include what? stdio. And I need to spell it correctly. That's the wonder of syntax highlighting, right? That if you don't spell something, you know right away because the color is off. If you don't have syntax highlighting, transpositions of letters can, depending on the letters, can be quite difficult because you've probably seen online before that somebody will screw up letters in a paragraph, but you can still read it. Why? Because our brains are good at correcting those things. And so if I see this, my brain is not good at correcting that transposition, but my brain is good at seeing colors. Include, at least those of us that are not colorblind. And then math.h. Why would I want to include math.h? If I'm going to use the quadratic formula, what am I going to use? Square root. And that's where? In the math library. Int main, int argc char argv, return 0. Great. Now I'm only going to indent 2 spaces. You just need to be consistent about it, okay? Now, do we want to do this interactively or non-interactively? You tell me. There's no right answer because we didn't specify over here. Of course, there is a right answer if it's specified in a handout or something like that. And if you're not getting, if you're getting seg faults or you're not getting the correct answers, probably, do I read them interactively or as command line arguments? So which one do you want to do here? All right, let's do it non-interactive. Here's another trick to do. Do the interactive version at home. Right? To do. Anytime you need to remind yourself, I need to do this, but I don't want to do it right now because I'm lazy, always put in a to do. And there are IDEs that will actually go out and find all these comments that have to-dos in them and collect them and say, here are your tasks that you have left undone. Okay, fine, I'm going to have to go back and do them now, right? So to do the interactive version at home. We're going to do the non-interactive version here. So int a is equal to the first command line argument, and I will convert that to an integer, argv sub 1. Why not argv sub 0? Remember that that's the executable program name, a.out. Right? If you happen to rename that, then it would inherit that new name. The real actual first argument provided by the user is argv sub 1. Cardinal sin right there. It's called copy paste and then change. We call that copy pasta. And why? Because it leads to spaghetti code. Not very good. What's spaghetti code? Well, it's like spaghetti, the cooked spaghetti. That is all that's all mashed together, and you can't tell one noodle from the next noodle. You've got code that's all mashed together, and you can't make heads or tail of it because it's disorganized. It's all one gigantic glob of garbage, right? So don't write spaghetti code. There are my first 3. Of course, I would have double root 1 is equal to, what's the quadratic formula? Help me out. Negative b plus minus square root of b squared minus 4ac. Is that correct? All over 2a? Is that correct? Lots of problems there, right? First of all, can you do this? No, technically you can't even do that in mathematics. That's not a function because it does not, it fails the vertical line test, right? Et cetera, et cetera. So we'll go ahead and take the root 1 to be plus, and then we'll have root 2 be the minus version of it. Okay? Now it's right. Do I have the caret in C? Nope. It would need to be b times b for b squared. Okay. 4ac, is that going to work? No, why? If you want 4 times a times c, what do you need to do in code? Asterisk, 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 asterisk. Okay? All right, fine. Now, is that correct? No, why? PEMDAS, right? What's the order going to be here? It's going to compute all the square root here. It's actually going to compute everything inside here first, then call the square root function. And then it's going to divide 2a, and then it's going to add in negative b over here. Right? Is that the correct order of operations? Nope. I want this entire thing on top. What's the thing on the top called? What's the thing on the bottom called? This is called the numerator. This is called the denominator. Right? And go ahead and 2 times a here. 2 times a on the bottom, likewise. Now that is correct. Once I balance all my parentheses. Is that going to compile if I forget a parenthesis? Let's find out. Oops. Nope. Why? Because it got to this point on line 22, column 49. It expected this closing parenthesis here that was not there. And so it's giving you a hint at where it failed to compile. Because I didn't, if you've got an opening parenthesis, you have to have a matching closing parenthesis, and it's all got to be well balanced. I can't have opening and closing with, oh, I could do that, but I'm not going to, like this. There, that's correct. All right? And then we can print out, printf, roots of %d x plus %d, or x squared, sorry, x squared plus x plus %d r %d and %d. End the line. I am providing 5 arguments here. In my kilometers to miles, I was providing 2 arguments to match the first and the second placeholder here. The placeholder order matters, so I would have A, B, C, root 1, and root 2. Right? Now let's see if this compiles. Oh, no, what's wrong? Actually, it does compile. Everything is just a warning. Right? Oh, nope. Oh, really? You don't know where square root is? GCC LM roots. Undefined reference to square root. No. Why are you complaining? That's just warning, warning. All right, well, let's see if it actually runs. A dot out. Give me 3 valid coefficients. 1, 2, 1. Oops. Oh, no, there's no A dot out. Okay, that's not working. Roots dot C. What do you mean you can't find square root? Fine. Like that? Okay, there you go. So I take back what I said before. Even on CS50, you do have to use the -lm flag. Garbage, but you have to do that. I don't know why. Your setups might be different. I don't know. Is anybody following along in their own CS50 and didn't have to do that? Okay. Well, my LM has to be at the end here, but so be it. Fine. When I did that, then it compiled. It's just complaining here about with some warnings, and those are intentional. We'll talk about those in 1 second here, or maybe next time since we're almost out of time. 1, 2, 1. Right? The roots of 1x squared plus 2x plus 1 are, whoa, is that the correct root there? No. You can pull out your calculator really quick and tell me what the roots are. I don't know what they are. But we'll have to figure that out next time. Right? As a take home until Wednesday, think about what might be going on there. Right? And hint, the warnings are trying to tell you something. All right? Okay. I will see you on Wednesday then.